All right, 9-1, day 1, we're starting a new chapter, last one of the year actually, so that is kind of fun. Really switching gears from matrices. Chapter 9 hits a variety of topics like sequences, series, and probability, as the title suggests, in that order as well. So we'll start today with the topic of sequences. So there's two different types of sequences we could look at, an infinite and a finite. It's essentially a pattern of numbers, which you can think of them as functions. We just only put in whole numbers. Okay, the notation that you'll see is, if you see a sub 1, that's your first term of the sequence. A sub 2 would be your second. Obviously, a sub 3 would be your third. A sub n would basically be an arbitrary term that we'll work on ways to find that, so we don't have to list off like all the terms in a row in a particular sequence. But sequences can go on forever, giving you the concept of an infinite sequence. We'll primarily work with, I guess, both, but mostly finite. But yeah, so two different ways you can kind of think about this. It's like a pattern of numbers. If you want to think about them like functions where we only put in whole numbers, that would work too. Alright, so here's a few examples of what we're talking about. I'm just going to find the first 4 terms of these. If I'm looking for the first term of a sequence, I put in 1 for n. When I do that, you can see that I get 1. All right. A sub 2, I put in 2 for n, and I do 2 times 3, which is 6, minus 2 is 4. To get the third term of the sequence, I put in 3, and I get 7. And a sub 4 is 10. Now check out these other two where you might find that the formula describing the sequence, because that first one is pretty straightforward. It actually looks very linear, right? Where each time it's going up by, each term in the sequence is going up by 3. You can come across some sequences that are a little more, yeah, they're a little different, not linear. But don't be fooled if you're finding any particular term. If I want to find the first term of this sequence, I'm putting in 1 for n. That comes out to be 2. If I want to find the second term of this sequence, I put in 2 for n. Might have noticed here that this one, so it has a pattern, and so it is a sequence described by that formula. It just hops back and forth between 2 and 4. Okay. The big idea, though, is you want to find any term in a sequence, put that number in for n. Like, check out this last one. Seems to have a lot going on, but that's fine. You could have multiple places where you need to put 1. Because it has n on the top of the fraction. And it has it on the bottom. Okay, so the first term would be -1. But I'm still following the other two examples where I see n, if I want the second term, that's where I'm putting a 2. -1 squared is just 1. 2 times 2 is 4. -1 is 3. Okay? So the first term was -1. Second term was a third. Let's get the next 2 here. Then we'll call it quits for this example. -1 to the third over 2 times 3 minus 1. Top goes back to -1. Bottom would be 5. +1 on top. So -1, 1/3, -1/5, 1/7. So it seems like those fractions are getting closer to 0, but then they keep swapping positive, negative. So another kind of interesting one. All right, this is something we'll explore a lot more as we progress through the chapter, but so those formulas that we just had, okay, to write an equation for them, here I'm giving you a couple ones that I think are a little bit more basic that you could figure out, but if you feel like these are a little tricky, we will get a lot more to help us do that, okay, to write the formulas, all right? Okay, first thing I noticed there is that on each one of those I'm adding 2. Okay, now for my first term is 1, second term is 3, third term is 5, fourth term is 7. Okay, each time it's 1 less than double. So I want to double it, but I do want it to be 1 less than, right? So for example, I saw here that the fourth term was 7, right? So if I were to double 4, that would be 8, minus 1 would be 7. Same thing happened with 5, that I saw that the third term of the sequence was 5. You know, double 3, we get 6, take away 1, and you got your 5. Here I'm going to look at the two parts separately, and I notice that nothing is going on the top. But check out the bottom. That's 2 to the first power. Second term has 2 squared. Again, I'm just looking at the bottom of these fractions. Third term has 2 cubed. Fourth term is 2 to the fourth. Fifth term is 2 to the fifth. On the bottom, it looks like it's 2 to whatever term in the sequence that you're in. Okay? Don't be surprised in the homework if you come across a couple of those that are a little bit more basic. I just want to introduce you to that idea of finding the formula for the sequence. Again, we'll get serious about doing that and have some better, more sophisticated methods for coming up with those formulas. All right, one more topic for today, and is that of the factorial. Any positive integer has what we call its factorial. Notation-wise, we put an exclamation point after it, so that's kind of fun. And it doesn't mean that you just scream n really loud. That would be kind of cool if that's what you did. What it means is you take every positive integer and you multiply them until you get all the way up to the integer that you are at. Notice for the definition, factorials only are used with positive integers. All right, let me just give you a quick little example. 3 factorial is 1 times 2 times 3. Okay, I stopped once I got to 3. I multiply all those numbers and I get 6. A special case that's a little bit tricky, but for all these numbers to kind of work out as they should, we define that 0 factorial is actually 1. So factorials will kind of show up throughout Chapter 9. Not randomly, they come up time and again because in counting principles and in probability, factorials just come up. This one I don't feel like doing the first 5. Let's do the first 4. Top would be 2. 1 factorial is just 1, so the first term of this sequence. Okay, notice I'm doing the same thing to get the terms as I'm just plugging in n. I want my second term. The bottom would be 2 factorial, but that would be 2 times 1. So that's kind of interesting. First term was 2. Second term was also 2. Let's take a look at the third, which will be 2 to the third. So 2 to the third is 8. Okay, so 3 factorial is 3 times 2 times 1. We saw that example, it's 6. 8 over 6, which would reduce to 4 over 3. So the third term would be 4 thirds, and our final one. Four factorial would be 4 times 3 times 2 times 1. That would be 16. All those numbers in the bottom would multiply to 24, or 2 thirds. Alright, we'll wrap up with these 3. I want to show you a few other expressions with factorials that we should be able to simplify. I want to show you how I do this. Because these could get really crazy to write out, and we don't necessarily want to do that. So what I would do is this. On the top, I'm going to rewrite that a little. I'm going to say 8. It's factorial, so it would be 8 times 7 times 6, but I don't want to write out everything from 6. 2 factorial is 2 times 1. And I'm just going to leave 6 factorial alone and watch what happens. Okay, the reason I stopped at 6 is I saw it was going to cancel nicely with the bottom. Now on the top I just have 8 times 7, that's 56. 2 times 1 is 2. That expression would simplify to 28. Part B, I'm going to do the same thing. So 2 factorial is just 2 times 1. I could have just written that as 2 times 6. Notice how I'm going to stop at 5 factorial. The 3 factorial I'll write out, but I'll leave the 5 because I know that's going to cancel with the top. And now the numbers I have left are pretty manageable. 2 times 1 times 6 is 12. 3 times 2 times 1 is 6. That whole expression simplifies to 2. Okay? Last one here. The numbers went away and the variables showed up. It's actually a fairly straightforward one, though. Okay, so on the top, I would start with n, but then watch this. The next integer after n would be n minus 1, right? Think if n was 8. You would do 8 times 7. Well, 7 is 8 minus 1, but that's all the farther I need to go because I like to write it out as a factorial once I have something that cancels with the bottom, and at that point I do. And all that's left over is the n that was on the top.